today we shall discuss few more properties of Legendre polynomial. Few properties of Legendre polynomial. As for example, the first property is what is PL of when x is equal to plus 1. Our starting point will be the expression for the generating function g of xt is equal to 1 minus 2xt plus t squared raised to the power half is equal to t to the power LPL of x. If we put x is equal to 1, this expression with x is equal to plus 1 becomes 1 minus 2t plus t square to the power minus half. This is equal to 1 minus t to the power minus half, and on the right hand side we will have t to the power L PL at x is equal to 1, or PL at 1 is equal to 1 minus t to the power minus 1. If we expand it in binomial series, since t is within the range 0 to 1, this will give you a convergent series. This is 1 plus t square and so on and so forth, which can be written as k is equal to 0 to infinity t to the power k. If we collect the coefficient of t to the power n from either side, we will have Pn at 1 is equal to 1. So the result is, this is plus 1. This is one property. Now coming to the second property, that is what happens to what is the value of PL at x is equal to minus 1. PL at x is equal to minus 1 is equal to how much? Again we put x is equal to minus 1 in the generating function, so we get 1. This is equal to 1 plus t to the power minus 1, which when expanded is t cube. This can be written as k is equal to 0 to infinity minus 1 to the power k t to the power k, and in terms of Legendre polynomial, this is summation over L t to the power L PL at minus 1. So if we compare the coefficient of t to the power n, then we get Pn at minus 1 is equal to minus 1 to the power n. So this is minus 1 to the power L. What happens to the values of PL at x is equal to 0, that is at x is equal to at the origin? We know that PL of for L is equal to odd is an odd function of x, so it should be 0 at the origin. But for even values of L, PL at x is equal to 0 is in general not 0. What is its value? This is the question. So with x is equal to 0, the generating function gives us 1 plus t square to the power minus half. So when we expand it, as we have done earlier, only thing is that we have expanded it z to the power minus half, then all the terms on the right is positive, and here the terms will be alternately negative and positive. Okay, it is from this expansion. and if we write this, we have this is L is equal to 0 to infinity t to the power L PL of 0. You see that for A, in the left hand side only the even powers of t appear. So for odd values of L, the PL is 0. PL is equal to odd at x is equal to 0 is equal to 0, and PL is equal to even at x is equal to 0 is. So this term contributes only when this is summation over m is equal to 0 to infinity t to the power 2n p of 2n at 0. So it is minus 1 to the power L 2L factorial 2 to the power L and L factorial square. You can check that we know that P2 is equal to 3x square minus 1, P4 is equal to 1 by 8, 35 x to the power 4 minus 30 x square plus 5. So at x is equal to 1, this is 1, and x is equal to 0, it is 5 by 8. You put, but L is equal to 4, L is equal to 4, we have this factor is plus 2L means 4 factorial by 2 to the power 4 into 2 factorial square. So this is 4 into 3 into 2. This much is 4 into 4 into 2. 4. 2 square is 4. If we this is simply 3 by 8 plus 3 by 8. So I have this is 25, 30. Sorry, it should be 3. It is 3. Note the correction. And this is the result. Now come to the property that what happens to if we replace x by minus x, so we get that P of L at 0, or we write this in this PL plus 1 at 0 is 0, and P of 2L at x is equal to 0 is minus 1 to the power L 2 to the power 2L factorial 2 to the power L factorial square. Now come to the parity of the Legendre polynomial. We have earlier seen that the Legendre polynomial of even order are even functions of x, while those of odd order are odd functions of x. So it will it has a definite parity. So parity of PL of x. So we are now going to address this. We see that the even for L even, PL has even parity, for L odd, PL has odd parity. How to prove this? That is, our question is to get PL of x, how it is related to PL of x. This is the question. So we write g of minus x minus t, which is equal to g of xt, because note the function 1 minus 2xt plus t square if we simultaneously change the sign of x and t, this function remains unchanged, that is. And if we write this as minus t to the power n Pn of minus x sum over n is equal to 0 to infinity is equal to sum over m is equal to 0 tm Pm of plus x. And if we collect the coefficient of t to the power k, then we find this is minus 1 to the power k pk of minus x is equal to pk of x, which leads to pk of minus x is equal to minus 1 to the power k pk of x. So the parity is p of minus l of x is equal to minus 1 to the power l pl of x. Now if we want to find out the values of the derivatives of the Legendre polynomial at x is equal to plus minus 1, say what is the value of PL of x is equal to plus 1. We write the equation that is satisfied by the Legendre polynomial of order L. The argument should be written. At x is equal to plus minus 1, 1 minus x square is equal to 0. So for x is equal to, if we write x is equal to plus 1, then this becomes minus 2 into 1 into PL prime at x is equal to plus 1 plus L into L plus 1 PL at 1. PL at 1 is 1. This is 1, which gives you PL prime at x is equal to 1 is equal to L into L plus 1 by 2. Then what happens to PL prime of x is at x is equal to minus 1? This relation again with x is equal to minus 1 becomes this, and this is minus this is equal to minus 1 to the power L. So we get PL prime at x is equal to minus 1 is equal to, this is L and there is another minus sign, so this is L minus 1 L into L plus 1 by 2. These are the few simple properties of the Legendre polynomial. Now we go to the multiple expansion or electrostatic or magnetostatic potential, vector potential. In electrostatic case, potential due to a point charge. We consider a point charge q to be located at r prime, the source coordinate, and our aim is to find out the potential at r field coordinate, and we use that is the r is equal to r minus r prime is the relative coordinate. Our aim is to find out the potential at P. The electrostatic potential at P is given by Q upon 4 pi epsilon 0 upon 1 by r. This is Q by 4 pi epsilon 0 . In our earlier course, we expanded this 1 by r minus r prime as 1 plus cos theta, where theta is this angle, inside. We expanded this in binomial series with the assumption that r prime is less than r. If r is less than r prime, the smaller of these two will appear in the numerator. 1 by r factor is there. Now we consider the term magnitude of capital R is equal to r minus r prime modulus, which is equal to r square plus r prime square minus twice r prime cos of theta, where theta is the angle between r and r prime as shown in this figure. For r greater than r prime, we take r common. This is actually there should be a square root. So this is 1 plus r prime by r whole square minus twice r prime by r cos of theta to the power half. This is for r greater than r prime, and this will be r prime 1 plus r by r prime, sorry, this much as if we take r common, this is 1 plus r prime by r whole square minus twice r prime by r to the power half for r greater than r prime, and this is r prime for r less than r prime. We write these two expressions as in general: r greater 1 plus r less r greater r less r greater times cos of theta, where symbol is obvious. R less means lesser amongst r and r prime, and r greater is the larger amongst this. So 1 by r can be represented as 1 by r greater 1 plus, I write this term first, Note that this value is within plus minus 1 and this is less than 1. So we can identify this as x of the generating function, and this is the parameter t of the generating function. With this we can write it 1 by r greater summation over L is equal to 0 to infinity r less by r greater to the power L and PL of cos theta. This is the actual expression that we were not familiar with the Legendre polynomial. In the earlier module we have written the expression in this form. Note that this is P1, this part is P2 and this is P1, 1 is P1, this is the expansion. So if we introduce the generating function of Legendre polynomial, the multiple expansion of electrostatic potential or the magnetostatic vector potential becomes very easy. As in fact, any quantity where any quantity is of the form r minus r prime can be expanded in Legendre polynomial in terms of Legendre polynomial. That's all so far as the theory of Legendre polynomial is concerned. We have completed the course on Legendre polynomial. In the next class we shall discuss few simple problems on Legendre polynomial to conclude the discussion on Legendre differential equation.